Welcome to Sanford Flip Math, the home edition. We are in the calculus course, and we've been working through the Larson Battaglia book. We're in the chapter that starts talking about integrals, antiderivatives, and the like. We are going to spend a bit of time starting to set up the area side of things. And to do that, we need to first talk about sigma notation. Sigma notation becomes part of how we keep track of what we're going to do for doing area, and I guess I could say areas, because that's how we treat area initially. At least that's how we think about it. Sigma notation comes from the Greek letter sigma, which is like our English S. It doesn't look like an S, it looks more like an E. So this is the capital sigma, this is the lowercase sigma. We're going to focus on this guy right here, the capital version. And it just means sum. In other words, add up. So get some fancy stuff to go with it. So we have this sigma here. This tells us we're going to index. That I is an index. We're going to index from the first term to the nth term, and all the way through we substitute in I values. Now, if this could be a different letter, this could be J, could be K. Those are the kind of the common go-tos, I, J, K. Could be any letter, but it's usually one of those three. Okay, and then you index counting by integers, by whole numbers, from whatever this starts with to whatever number this is. So if I have a sub I, then I'm going to have a sub 1, a sub 2, a sub 3. So the first term plus the second term plus the third term plus etc. until I get to the nth term. Okay, so the index is where we are. It can also be a number that gets substituted. Okay, so just as a quick little example to clarify this notation, we're going to start at 1 and go to 6 for 3i plus 2. So the first term is going to be 3 times 1 plus 2. The second term is going to be 3 times 2 plus 2. The third term is going to be 3 times 3 plus 2. And so what I'm doing is I'm literally substituting these values in. I got to keep going until I get to 6. So we're at 1, 2, 3, 4, 5, 6. You know, it's very high tech, but so this is intended to be a compact notation to represent all of that. And then we need to just add this up. So this is going to be 5 plus 7 plus 9 plus 11 plus 13 plus 15. No, this is wrong. Oh, poopy. Sorry. 8. I went a little too fast there. 17, 20. Let me just double check this last one. 3 times 18 is, or 3 times 6 is 18, plus 2 is 20. Yes, I was going up by 2s and I was supposed to be going up by 3s. Oops. So to total this out, because that's literally what this is asking you to do. So I have 13, 24, 28, 38, 45, 55, 65, 75. That's it. Okay. Number 2, same idea. This other example is just now we're starting at 3 instead. And notice this one is k from 3 to 9. So this is going to be 3 squared plus 1 is where we start, plus 4 squared, and you just increment by 1s. 5 squared plus 1. 8 squared, 9 squared plus 1. Okay, and then we need to add all of that up. Okay, so through the powers of technology, this ended up 10 plus 17 plus 26, and all of that added up to 287. Okay, so again, sigma notation, it's sigma like S for sum. So sigma looks like an E, but it's really not, is like S for sum. In other words, just add them up. That is literally all it means. Okay. All right, so I'm going to the next. Okay, so the reason we're going to do this is because we are going to be adding up areas to find areas. What we're going to try and do is look at ways to find the area between a graph, between a curve, and between the x-axis. I'm sorry, between the curve and the x-axis. Okay, so right now we're going to approximate area. We will let this evolve into finding an exact area. So it will get there. It's going to take a minute. Okay, so what we're going to do is take a curve. So I'm going to work from this example and then I'll refer back to these ideas. But the idea is we're going to be putting rectangles between a curve and the x-axis. Okay, so we're going to use rectangles. Are rectangles the only way to do this? No. Is it probably the most straightforward way? Yeah. And if we use enough rectangles, it'll be a pretty close approximation. Okay, so rectangles can be inscribed inside a curve. So inscribed, the idea is, so if I go, so if I'm trying to find the area between this parabola and the x-axis, and I'm going to find that area between x equals 1 and x equals 4. So these are x values. Okay, so I'm going to go from 1 to 2, 3, 4. I'm looking at approximating this area. Now, if this was a circle, we have a formula for that. If this was a triangle, we have a formula for that. If we have, if this was a rectangle, we have a formula for that. But the problem is it's a parabolic shape, which is not really a circle. And so that makes this a little more interesting. Okay, so I'm just trying to really make it obvious what I'm finding the area for here. Okay, so that guy right there, that little piece. Okay. So what we're going to do is use rectangles, as I said, to do this. Now, is that the perfect thing? No, it's not. An inscribed area would be all of the rectangles are inside. That's funny, I wrote insided. That's pretty hilarious. All of the rectangles are inside the curve. So for instance, what I'm going to do is see how I've broken this out. I have x equals 1, 2, 3, and 4. N equals 3 means I'm going to use 3 rectangles. Okay, so the rectangles, though, have to be off of the sides delineated by these lines, because notice I'm using 3 regions here, 3 little intervals. I'm going all the way from 1 to 4, but I'm counting by ones in essence. Okay, so I'm going to do the middle one first, just to make it a little more obvious. But when I go up here, I hit the curve. When I go up here, I'm hitting the curve. And if I'm going to go inscribed, I need to make my rectangle off of the points that make the rectangles inside. Well, this guy hits on the right side, and it's going to be more like that. So I have a rectangle here, I have a different rectangle here, and this rectangle doesn't even really have a chance to go anywhere because it's the inside height would be on the left side. The outside height would be up here, and that would not be inscribed. So what I'm going to do is add up these rectangles, and so the area of this rectangle is going to be the width of 1 times the height of 0. Okay, are you going to focus for me, please? Focus. Sorry. Okay, so this little rectangle has a height of 0 and a width of 1. This rectangle has, again, a width of 1 and a height of, in this case, whatever the x value gives us as a y value at 2. Well, just for our reference, I threw a little table over here, and that just came from putting in, again, 2. So 2 squared is 4, make it negative. 2 times 6 is 12, minus 5. So this is 8 minus 5 is 3. So that's where that came from, okay? So times 3 plus the width of 1 times this height to be inside is going to be from 4. Well, it turns out 4 gives us 3 again. Okay, so the inscribed area is going to be 0 plus 3 plus 3. Sorry, that's bugging you. I know, I'm sorry. Equals 6. So this would be a lower estimate because it's obviously it's not the full area between the curve and here. It's a lower estimate because everything's tucked inside the curve. Okay, this is not the only estimate. We could do an upper estimate, and in this case, the upper estimate would be circumscribed, and I think that's always the case. So circumscribed, scribed just means drawn, circum means around, and the idea here is the rectangles are on the outside of the curve. So when I'm going from 1 to 2, I'm going to go with the higher height. So it's going to look like this. When I go from 2 to 3, I'm going to go with the higher height. It's going to look like that. When I go from 3 to 4, I'm going to go with the higher height. And again, I'm just going from 1 to 4, so I'm done. Okay, so the rectangles now go outside the curve because, again, we are circumscribing. We're going outside the curve. Okay, so this time from 1 to 2, again, the rectangles are 1 wide, and the height is based on 2 this time, and we said 2 was 3. And from 2 to 3, that width is again 1. Okay, so we're doing a delta x times the y value. That's what we're doing, because we're getting the width from the change in x, and the height is that y value. Okay, plus the next one from 2 to 3 again was 1, but the height is based on 3 this time, so that's 4. So we're talking about the different ways you can do these approximations. So for 3 to 4, again, it's 1 wide. And the height of this one, again, on the outside still happens to be at x equals 3. So this is going to be 3 plus 4 plus 4, which is 11. Well, there are a couple other possibilities that we're going to talk about right now. So you can do a lower estimate, which is inscribed. You can do an upper estimate, which just means bigger, which is outside. You can do a left RAM. RAM is rectangular approximation method. You can do left RAM. It's also called a left Riemann sum. I'm guessing Riemann is dude's name. Okay, those are the same thing, left RAM and left Riemann sum, which means you always take the left. So it's going to look like a blend of the two we just did, but it's always going to be from the left. So I go to the left side, I go from 1 to 2, that width is still 1. I go to the left side of it, and it goes up to, okay, it doesn't go up at all, it goes to 0. Plus, from 2 to 3, the width is 1. So now I'm going to stay on the left side. So I'm on the x value 2, and that's going to be 3 for the y value. Same idea from 3 to 4, the width is 1. And again, I'm staying on the left side. So from x equals 3, that's a y value of 4. Okay, so this is going to be 0 plus 3 plus 4 equals 7. Now, is that an upper estimate or a lower estimate? Yeah, it happens to be somewhere in the middle. Well, that doesn't always mean it's better. It just means for this particular shape, for this particular curve, it happens to be in between the high and the low. Okay, one more. Right RAM. So right RAM is a right Riemann sum. I'm guessing somebody says Riemann, but I've never heard it. And he's not around, so we don't really know. So a right Riemann sum does the same idea. Again, this width is 1. And it just goes on the right side. Okay, so if I'm going from 1 to 2, that little chunk, then I'm going to use the 2, and its y value is 3. So that's the height of that rectangle. Okay, from 2 to 3 is 1. And I'm going to go on the right, so I'm going to go from 3, so that's 4. And then from 3 to 4, again, has a width of 1. So we're not using 1, 2, 3, and 4 as values 1, 2, 3. You know, we're using the width of each one of those little baby rectangles. So they all happen to be, in this case, 1. Okay, because I'm using easier numbers to work with. That's my goal. Okay. All right. And then the last one from 3 to 4, again on the right. Well, 4 on the right is going to give me a height of 3. And this time, this is going to be 3 plus 4 plus 3, so 10. Okay. All right. If you have a function that is strictly increasing, so in other words, it's going up. Oh, and I'm off screen, sorry. If I have a function that is going up, strictly increasing means it's never decreasing and it's never at a height of 0. It doesn't have to be linear. It could be curved, could be a parabola. If I have something strictly increasing, and if I draw left RAM, also known as left Riemann sum, if it's strictly increasing, then left RAM will be equal to the inscribed, which is the lower estimate, if it's increasing, because that's just happens to be where the corners hit. I don't think you want to memorize these ideas. I'm just throwing them out there for food for thought. If I have something that is strictly decreasing, okay, so it's going down, then it turns out that right RAM, if it's decreasing, then right RAM is the inscribed or the lower. Okay, and I guess the inverse of those, the opposite of those would be true. So if I had the increasing, then right RAM is the circumscribed, that was funny. Or in other words, the upper. Okay, and then same idea here. If I went left RAM on decreasing, is the circumscribed or upper. All right, so that's a lot of stuff to digest all at once, and the trick will be being able to draw those. You need to be able to draw all of those and calculate all of those. Okay. All right, so let's do another. We're just going to do one more example. Okay, and then we're going to call it good. Okay, so I know we're already getting there on time. I apologize. We're almost 20 minutes now. All right, so here we go. So what we're asked to do is an unknown number of rectangles. And just one second. Okay, so they want us to do upper and lower sums. Let's do a little sketch of this graph so we know what's going on. And the problem is that they're telling us an unknown number of rectangles, which is going to be a little bit annoying. 9 minus x squared from 0 to 2. So here's 0 to 2. 9 minus x squared goes up to 9 and does a lovely parabola like this. But again, we're just going from 0 to 2. Okay, so we're going from there to there. Okay, I'm going to draw some rectangles, and then what we'll try and do is set up the math based on that. Okay. Okay, so what we're asked to do a couple of things. Again, I don't know if I said this, but we want an upper estimate and a lower estimate. Now, worth noting that the section I'm looking at is strictly decreasing. Okay, so if I don't include the 0, it's x equals 0 itself, where the slope is 0. From 0 to 2, from the x value 0 to the x value 2, it is strictly decreasing. As soon as I step off the 0, I'm decreasing, I'm going down, even if I do a tiny bit. Okay. All right, so if I do an upper estimate is supposed to go out above the curve. Now, again, I don't know how many rectangles to draw. I'm just going to illustrate some just so we can get an idea of what's going on. Okay, so right now I drew 4. Okay, so this is n equals 4. And again, just to get the idea. So my first question is, how wide are these? Well, if I do the entire distance 2, the total change in x is 2. And if I divide by 4, because there are 4 of them, each one is 1/2 wide. So if I take that same logic, because I don't really know what n is, if I take that same logic, I'm going to do 2 minus 0. Okay, I'm going to call that b minus a. Okay, so I'm going from a to b. Right? I'm going from a to b. If I take the same logic, the distance between those two would just be the subtraction. And if I divide by, in this case, I divided by 4. Well, in this case, I'm going to divide by n. And so this is the width of every rectangle. Okay, this is going to get a little technical, so stay with me. Okay, so the area of one rectangle, is going to be the width of that rectangle divided by how many rectangles I have. Okay. Now the height of this rectangle, if I'm doing an upper estimate, I want to be on the left side because it's decreasing and it's going to go out. Okay. So what I need to do then is I need to start at the first x value, which in this case is 0. Okay. So I would say a. Okay. And then that a, I guess I need the y value for that a. So I need f of a. Now, this is where the crazy is going to start coming in. And it's going to be better if I have numbers, but this is just for the first rectangle. Then I need to, for the next rectangle, I need to add on some. Okay, so in our case, we're going to do 2 minus 0 divided by n. So 2 over n is the width of the rectangle. And I need f of, I'm going to start at 0, but then I'm going to need to step through here because what I'm trying to do is capture the formula for each rectangle. I mean, I could do this for the 4 rectangles pretty straightforward. I would literally do 1/2 is the width of one rectangle times the y value, which is 9, plus 1/2 times which is the width of the second rectangle, times the y value at 0.5. So I would do 9 minus 0.5 squared, plus, and then I would do that again. 9 minus the next x value is 0.25. I'm sorry, the next x value is 1. I was thinking about that 0.5 squared, plus, and I would keep doing this, right? 1.5 squared, plus, and I would do it again. Okay, and I would add those up. Well, what I'm trying to do is represent this when I don't know how many rectangles. And so it's not going to be this 0.5 every time. Okay, so it's I need a way to represent what's happening with these x values. So like this x value is 0.5, this x value is 1, this x value is 1.5. How do I represent an incremental x value when I don't know how wide they are? Well, I kind of do know how wide they are. They're 2 over n wide. Each one of these is 2 over n. So the first one's going to be 0. The next one's going to be 2 over n because it's going to move 2 over n over. The next one's going to be 2 over n times 2. The next one's going to be 2 over n times 3, etc., until I get to 2 over n times n. That's going to be the whole thing. I know this is feeling a little disorganized. I apologize. So these are the x values. So notice how this this part is going up by ones. Right, I started 0 times 0. Well, this was 0. I could have made this 2 over n times 0 there. That makes more sense. Okay, you're going to focus there. Oh, come on, focus. Thank you. 2 over n times 0 plus 2 over n times 1, 2 over n times 2, 2 over... These are just the x values. So this becomes 2 over n times wherever I am in the sequence. Well, that where I am in the sequence is the index. You can call it I, you can call it K, you can call it J, whatever. Okay, so this now becomes, this again is the width of the rectangle. This is the width of the rectangle, and times I tells me where I am in this picture. And then this says I want the Y value there. All right, so let's do this again. Only now I'm going to use the summation notation. I'm going to represent this big time. All right, so I have the width of the rectangle. I'm going to plug this into my original equation. Okay, so the width of the rectangle times the height of the rectangle, which is going to be 9 minus x squared. What's x? X is this. So this is going to be 2 over n times I. And so what I want to do with this is I'm going to add them up, starting with, in this case, I want to start with 0 because I want my first x value to be 0. So 2 over n times 0. So just kind of plug that in, and if 1 wouldn't work for this. And then it will increment by ones. So it will do times 0, times 1, times 2. Okay, so that creates this. And how far do I want this to go? I want an unknown number of rectangles, so I'm going to call that n. So this is the upper estimate. This is LRAM. This is a left Riemann sum. Excuse me. How would it be different if I want the lower estimate? Well, the lower estimate starts on the right side of every one of these rectangles. So really, I just need to shift the whole thing 1 to the right. And the easiest way to shift this 1 to the right is to shift my starting point. So I start with 1. This is going to be magical. I still don't know how many rectangles. And then the rest of this is just the same. Now, I'm sure there's a way to clean up how this looks, but I'm not going to do that. Is that it? Oh, I need that to be squared. There we go. Okay, so this is my x value being squared. All right, well, I think I need to leave it there. It feels like that was a lot. So we will talk in class about this. Remember, this is not meant to be a standalone. This is meant to get your foot in the water. So again, this was a lower estimate. Right RAM, in this case, right Riemann sum. Okay. All right. Well, thanks for being here. I know this is crazy. The notation is the thing that's weird right now. And just rest in the fact that there'll probably be like one question on the whole AP exam about the notation itself, because we're using this as a building block to go somewhere else. Okay. So don't get too freaked out. Yes, it will be on our test, but it's not going to be crazy deep, and there won't be a million questions like this. So, all right, much love to you. Thanks for being here for SanfordFlipMath, the home edition, and we'll talk to you later. Bye.